We are rolling. Hey everybody, today we are going to explore the heart. Now we have a sheep's heart here, which is approximately the size of a human heart. The human heart is about the size of a man's clenched fist, so a little bit larger than mine, which is pretty similar to this size. The heart beats 100,000 times a day, which is a lot of activity that we ask it to do. And so we want to make sure that our hearts stay nice and healthy and function optimally. The first thing that we want to do is orient ourselves to this heart. So looking here, we are looking at the anterior surface of the heart, with this being the left side and this being the right side. You can see that the left ventricle, which is the inferior portion, is much larger than the right ventricle, which is this more sort of superior portion. The ventricles are going to be the inferior part of the heart, like this that I'm covering up. And then the atria are up above them, with the great vessels exiting here. Also, the apex of the heart is this sort of pointed inferior angle, and the base of the heart is the superior portion where the great vessels are entering and exiting. You can also see that the heart is surrounded by fat. The fat is very firm in this specimen because it's been preserved. In the live specimen, it's going to be a little bit more flexible and pliable. This is important for protection for the heart. However, you don't want to have too much fat accumulating around your heart because that decreases the heart's ability to do its work as well as it might. I'm going to remove some of this fatty tissue so that we can get a better view of these structures that lie underneath. So I'm just going to remove some of this fatty tissue, trying not to injure any of the more delicate structures below. See, I did cut a little muscle off there. All right, so I've removed some of that fatty tissue that is on the outside. Some of the other surface features that we can see are the interventricular sulcus here, which is in between the left and right ventricle. And you can see how that's full of fat. Underneath this fat are arteries and veins that are supplying the actual cardiac muscle and then taking that blood back. So these would be considered the coronary arteries. They are in between the atria and ventricles. We have the atrioventricular sulcus, and then in between the two ventricles we have the interventricular sulcus. And all of those are full of arteries and veins that are supplying and draining the heart muscle itself. Then we have larger structures that are bringing deoxygenated blood to the heart and removing oxygenated blood from the heart. So when we're looking here, we have left ventricle, right atrium, left atrium. And here we've got the superior vena cava, which is bringing deoxygenated blood into this right atrium. So I can kind of put my finger or put the probe into that right atrium. So the first cut I'm going to make is going to be through this superior vena cava into the right atrium. All right, so you can sort of see this atrium if I open it up right here, and there are some muscles in the wall of the atrium, which are the pectinate muscles. Yeah, pectinate muscles. And then if you're lucky, you can see the fossa ovalis, which is the remnant of the foramen ovale, which is the hole that connects the left and right atria in the neonate during development. And then when the baby is born and takes its first breath, the pressure of the pulmonary system increases and it shuts off that foramen ovale, and then you get this sort of little scar of the fossa ovalis. Next, I am going to cut down into the right ventricle. All right, so now you can see that our right ventricle is open, And this is beautiful. So the walls of the right ventricle are relatively thin. They might not look it right now, but when we open the left ventricle, you'll see the difference there. And then you can see, do you want to just hold this open for me now?
Yeah.
All right, so here we can see the leaves of the tricuspid valve.
Oh, that's cool.
So on the right-hand side, we have the tricuspid valve, which is the valve in between the atria at the top and the ventricle in the bottom. And this is a beautiful picture of the pectinate muscles in that atria. So the valves are connected by these cords, which are called chordae tendineae, and they're connected down into the papillary muscles. So the papillary muscles contract and pull on the cords so that when the ventricle is filling with blood, the flaps of the valve, the tricuspid valve, can go back and cover one another, but they can't reverse into the atria, therefore keeping the blood in the ventricle and making sure that we have blood always flowing in the same direction. So blood here is going to come from the superior and inferior vena cava into the right atrium, flow through the tricuspid valve into the right ventricle. Now, from the right ventricle, I'm going to turn a little bit. In the uppermost portion of the right ventricle, which you can see sort of up in here, we have a narrowing called the conus arteriosus, which brings us to our pulmonary valve, and then the pulmonary artery leaves the heart, bringing deoxygenated blood from the right ventricle into the pulmonary circuit. So remember that the superior and inferior vena cava are bringing deoxygenated blood into the right atrium, then the right ventricle, and then it is going to flow out of the right ventricle, up through the pulmonary valve, into the pulmonary arteries, and then into the pulmonary circulation. In the lungs, the blood is going to become oxygenated, and then that oxygenated blood will be sent back to the left atria through 4 pulmonary veins. Now, I know what you're thinking. Arteries carry oxygenated blood and veins carry deoxygenated blood, but that is not true. Arteries carry blood away from the heart and veins carry blood toward the heart. So in this one instance, we have arteries carrying deoxygenated blood away from the heart to the lungs and veins carrying oxygenated blood from the lungs back into the heart.
That would be a great quiz question.
That would be a fantastic quiz question. Dr. Mel is always good with the quiz questions. Okay, so now I'm going to cut through into the left atria and then down into the left ventricle. All right, so now we are opening the left ventricle. Look at that beauty. So,
That is a beauty.
Mel, I'm going to have you hold here again for me.
Okay.
And I'm going to grab my pointer. So you can see here, these are the cusps of the mitral valve. So the tricuspid valve that we saw between the right atrium and the right ventricle had 3 of these cusps, and the mitral valve on the left side of the heart only has 2 cusps. Again, we have the chordae tendineae. I am going to go ahead and cut that in order for us to be able to open this a little bit further.
Very nice.
Sorry. And what we can see on the inside of the ventricle are all of these trabeculae carneae, which is the ridges of muscle inside the ventricles. We again have the chordae tendineae with the papillary muscles to keep these from backflowing. And you can see how much thicker the wall of the left ventricle is here versus, if I turn us back over, those thinner walls of the right ventricle.
It's quite different.
Now, why is it different? I would say that would be a good quiz question.
Absolutely.
The difference is that the right ventricle, which is smaller, is only pumping blood to the lungs, whereas the left ventricle has received that oxygenated blood back from the lungs and it has to work to pump this blood back out to the entire body. So it needs a lot thicker muscular walls in order to create enough pressure to overcome the aortic valve and push the blood through the aorta and out into the systemic circulation. Now, the last thing, when we look at the top of the heart here, we see the vena cava, which is kind of collapsed on itself, and then we see the aorta, which has this nice thick tunica media, nice muscular walls, and it stays open. So I'm going to cut into this aorta and see if we can find the aortic valve. So there are those beautiful cusps of the aortic valve.
That looks great. Yeah.
These are semilunar valves, so instead of having the chordae tendineae to keep them from retrograde flow, which would be flow in the wrong direction, they set together and close and support one another to hold closed.
Yep.
That's beautiful.
That is fabulous.
Here I have my probe in the aorta. It is coming out in the left ventricle. So oxygenated blood is going to flow from the left ventricle through the aortic valve that we see right here and out the aorta into the systemic circuit. Let's just consider for a minute the layers of the heart. So the epicardium is adhered very tightly. You can see this membrane is adhered directly to the heart tissue itself. And this is also the visceral pericardium. And remember, the parietal pericardium is going to be a second layer of that serous membrane. And in between the visceral pericardium and the parietal pericardium, we have the pericardial cavity. And because they're serous membranes, they have a slight watery secretion that keeps them from adhering together and allows the heart to expand and contract during pumping without having adhesions that form between those two layers. So that is, again, the epicardium. And then the myocardium is this large middle muscular layer of the heart here, and that's made up of cardiocytes, our cardiac muscle cells. This is endothelial tissue, which lines the heart and blood vessels, and in the heart we call it the endocardium. So we have the epicardium, the myocardium, and the endocardium here. Thank you so much for joining us today in our exploration of the heart. The heart is a fascinating organ. We invite you to join us for an exploration of physiology in our additional heart videos.